Okay, so the last section that we are going to talk about that is combined is volume and then volume by discs and washers. So we're going to talk about volume by cross sections, which is basically just slicing an object and taking multiple items over a series of a specific area. So when we talk about volume by cross sections, essentially what you're doing is finding the area between two curves and then extending that to find the volume of a solid. So the idea is to divide the solid into thin slabs. So if you take a sphere and you cut a slab out, this is what they're talking about. And then you would take essentially something like this, which would be your slab, and you would line multiple ones up, one after another, which would then create this volume. So just imagine like multiple slabs like this. And the idea is to use the approximations using a Riemann sum, and you would essentially have all of these together. But we actually have a formula which helps us to avoid using the Riemann sum. So there's multiple ways that we can do this. We can do it by a sphere or a right pyramid. Okay, so then here essentially this looks like a square. And then a right circular cone, so then we would have a circle, and you notice the radius is, or even the diameter is different all the way through. Or you could take the same shape and cut it vertically, which would essentially have right circular cone slabs which almost look triangular in shape. So if we let S be a solid that extends along the x-axis and is bounded on the left and right hand side, okay, so this would create the area between two curves. And then we have these planes that are perpendicular to the x-axis, and you have your bounds of x is equal to a and x is equal to b. We can essentially find the volume of this solid, assuming that we have a cross-sectional area and we know what it is over that given interval. So what they're saying here is that the volume of a solid can be obtained by integrating the cross-sectional area from one end of the solid to the other. So what they're saying is, if here I have the area between the two curves like this, okay, so this is one curve, okay, and then essentially this is my other curve, all right, so we're bounded by the x-axis, and then we say from A to essentially B, which is going to bring me all the way down this way. This becomes a three-dimensional shape. So we have the area top minus bottom, and then we have a cross section here. We would say that this is rectangular in shape like this, and now this is coming up from the paper, so creating that three-dimensional shape. So you are integrating the area between the two curves and the area of this cross-section, which they're going to say is, it could be anything. It could be a semicircle, it could be a triangle, it could be a rectangle. So they're using a rectangle here, which is very simple. And you're going to have multiple rectangles from A to B, which would then be lined up side by side by side. So then you would have another one here, and then another one here. And because I don't know how many, I would say I'd have n rectangles from A to B, which would then create that area between the two curves. So what we have is the volume formula. So this is really important here with the volume formula. So it says, let S be a solid bounded by two parallel planes that are perpendicular to the x-axis. Okay, so what that means is perpendicular to the x-axis means that we would have y is equal to something, and it's going to be a dx problem. Okay, so y is equal to some given function, and this will be a dx problem, and then you have your bounds of x is equal to a and x is equal to b, and then you have the cross-sectional area here. okay, which would be perpendicular to the x-axis, is given as a of x. So what you have to understand is this cross-section could be anything. They're going to have to tell you what it is, but it could be anything. We have specific shapes that we use, but it could be any shape. So the volume here is the integral from a to b of the area, which is basically going to be, in this case, because it's with respect to x, this will be a top minus bottom situation here. So this would be the top minus the bottom, and then for the area of a rectangle, it's going to be base times height, and I'll show you the exact application, but it would be put into the area formula of the cross section, and then you have dx. So remember here, this will represent your height, this would represent your width, this is from the left, and this is from the right. So this right here is extremely important that you know, and what you're doing is you're taking the cross section, taking the area of a cross section across the entire area. Okay, so you're taking the area of the cross section across the entire area between the two curves, okay, to find the volume.